So Matti, it's time so we can start. So welcome to the second part of Professor Matti Lassas' talk. And so over to you, Matti.
Okay, thank you very much. Yes. So thank you for everything. Yes. So let us continue. And let me recall what type of problem we were considering. If you assume that we have some point sources in the medium, and now we assume that in the medium the wave speed is varying, and we model this as a manifold. But in principle, this could be any compact Riemannian manifold with non-empty boundary. So if you have a point source that becomes active at time t is equal to 0, it sends a wave, and this wave is observed at different boundary points. And this way we can see that what is the travel time distance from the source point x to the boundary point z. And this gives us the boundary distance function Rx of z. So that is just the distance from interior point to a boundary point. And this is geometrically interesting question itself, that if we are given the collection of all boundary distance functions, let me recall that this. So let's see how this. Yeah. So let me recall that this. These boundary distance functions, they are continuous functions on the boundary. If we know this family, can we reconstruct the manifold and the metric on it? Physically, this would be a closely related question if we would know that there are lots of point sources, so that they approximate the case when we have a point source at arbitrary point of the manifold. And indeed, Kurilev was the first one who considered this. He was considering the topological structure and had also had some results for metric structure, and then with Kachalov and Kurilev we considered the differentiable structure and the metric tensor. And this also works for non-compact manifolds. Let's see how this result is proven, and we are considering simple manifolds. But let's first start considerations on general manifold, which has no simplicity assumptions. And so for point x, the boundary distance function Rx of z, this is the distance from x to z. So we consider distance from x to different boundary points. And the mapping that maps manifold to corresponding boundary distance functions, this can be considered as a embedding of the manifold to continuous functions on the boundary. Here is actually an interesting point that often differential geometry one wants to embed a manifold to relatively low dimensional Euclidean space. Now we do something else. We have infinite dimensional space, but because the manifold itself is unknown to us, we are only given the boundary. We don't know what the manifold is. So we want to embed the manifold to a known function space. So this collection of all boundary distance functions, it is considered as a subset in continuous functions on the boundary of the manifold, and it turns out that this is actually isometric image of the manifold M. And let's consider why is this. Let's first show that this mapping from point to corresponding boundary distance function is continuous and Lipschitz one map. This comes from the triangular inequality, like in this picture. If we have any 2 points x and y inside of the manifold, so then the difference of the boundary distance functions, this is by definition the difference of distances from x to z and y to z, like here. And by triangular inequality, this is bounded by the distance of x and y. When we take maximum over z on the boundary, we see that the norm in the space of continuous functions, so the subnorm of two boundary distance functions, difference of two boundary distance functions, this is bounded by this distance. So this means that the mapping that maps the manifold to this continuous function on the boundary. This is continuous map, and it is Lipschitz 1 map. And also, and so also in general case, we can consider this map as embedded. Let's consider now to simpler case when we assume that the manifold is simple, or something that is a little bit generalization of simple. Namely, let us assume that all geodesics on a compact manifold are such that they are shortest curves between arbitrary points of the geodesic. So this is to say that geodesics are assumed to be globally minimizing curves. They minimize length between any point. Okay, what happens then? The manifold is compact. So if we consider the geodesic that starts from X and goes to Y, this geodesic continues because the manifold is compact. The geodesic cannot be infinitely long. So it hits the boundary at some point Z0. And by our assumptions, all geodesics are distance minimizing curves. So this geodesic is minimizing from X to Z naught and Y to Z naught. So let's see what happens. We have in this the distance from the distance from Z0 to Y plus distance from Y to Z is equal to distance from X, distance from Z0 to X. So we get this identity. And this now means that if we consider the supremum of the difference of the boundary distance functions, the supremum is always larger than the evaluation of the difference of boundary distance functions at some particular point. That we use this Z0 here. This here, by definition, is the difference of these two distances. And by the earlier equality, this is the distance between X and Y. So we see that the supremum norm of the difference of two boundary distance functions is larger or equal to the distance of the points. This is the opposite inequality. Let's go to earlier slide. Oops, let's see how. For some reason it's difficult. This earlier slide is here. So here we had the opposite inequality that came from the triangular inequality. And here we have the same inequality with different, just the opposite relation. So we combine these two and we see that the difference of two boundary distance functions, its subnorm is equal to the distance of the points. So this means that the original manifold with these distances and the set of the image of Rm, the set of all boundary distance functions with subnorm, those are isometric. So what this means? We consider the mapping R that maps point to corresponding boundary distance function. It maps manifold to this subset R of M with the space of continuous functions. This is isometry. So actually our data, this collection of all boundary distance functions is an isometric metric space to the original manifold. And this means that we have reconstructed the original manifold. So this is how this kind of observations, when we have observations from the point sources, we collect all of them together. Then we can reconstruct the isometric copy of the original manifold, which means that we have reconstructed the isometric type of a manifold. This is what reconstruction of a manifold means, that we construct an equivalent isometric manifold. Okay, any questions on this part? Okay.
Matti, just one question.
Yes, please.
So you are not assuming tangential grazing of the geodesics? Is that part of the assumption?
Let's see. Yes. So here, yes, here we don't need convexity. Yes, in this argument we don't need strict convexity. That the geodesics could. Yes, actually, so in this argument, the manifold does not need to be convex. That's true, yes, yeah. So in general, this result is true with all compact manifolds. So this is a little bit more general than a simple manifold. Did this answer the question?
Yes, but then the distance could be, so then how is the distance well defined then? Because let's say if you have a kidney-shaped domain, how would you define the distance then?
Let's see. So then we define this. So we define the distance that we take piecewise smooth paths between any 2 points of the manifold, and then we take infimum over those. So when we consider if we consider the length minimizing paths, they can be such that they are geodesics inside the manifold, but they start to follow the boundary if the boundary is non-convex.
I see. Okay. All right. Yeah. Thanks.
An excellent question. Yes. Actually, when you want to do differential geometry for manifolds with boundary, the non-convex boundaries always cause huge problems in somehow and technicalities. So that is actually a crucial question. So thank you very much. Okay, let me move to this. We studied first that why these nonlinear equations are interesting from the point of view of inverse problems. Then we somehow showed some basic tools how we can use those. And let us now go to the more recent topics and see what type of results are actually done just at this moment. And for that, let me consider now a metric that depends on both on space and time. So more mathematically, let's just consider Lawrencium manifold. So Lawrencium manifold is a manifold where we have a metric tensor that is very similar to Riemannian manifold. But the metric tensor, if you consider it as a matrix, it is not positive definite. And for instance, and as an example, is that we could take this type of metric where this G0 zero component of the matrix is negative. So generally, Lawrencium metric is a metric where that is given by matrix which one eigenvalue is negative and all other are positive. And so this is one typical example. And now I use the convention that the time variable time is denoted by x0. So the coordinates run from 0 to n. x0 is the time coordinate, and the other are considered as spatial coordinates. And let us now consider like a general manifold of dimension 1 plus n is larger than 2. And let's first start with the nonlinearity that is polynomial of degree m. The Lorentzian wave operator is defined with a very similar formula than that is used for define the Laplace operators. But now the metric is not positive definite. It has one negative eigenvalue. So this operator is actually hyperbolic operator. So that's why we denote it by box G. And then we consider again a simpler model of nonlinearity where we have a linear wave operator plus then nonlinearity u to power m. And now we assume that the metric G is unknown, and that's why we have here just coefficient 1. So metric is here unknown. Let me consider some definitions on Lorentzian geometry. So the geodesics are actually now defined with the same differential equations that was used in Riemannian geometry. Then a vector psi with a base point x. This is called time-like if the quadratic form defined by the metric tensor. So every metric tensor is a matrix. It defines a quadratic form. If the metric defines a quadratic form evaluated at psi gives negative value, then we say that the vector is time-like. It means that the vector is pointing inside the light cone. And and vector is lifelike if this quadratic form gives value 0 and psi is not 0. So this means that the vector is tangential to light cones. Also, the light cone has two components, future part and past part, and the future light cone is denoted by L plus of x. Then there are some causality-related definitions that are widely used in general relativity. When we have a point P, then all points x in the manifold, or the manifold is now the space-time. So if x is in the causal future of P, we denote it by J plus of P. In this picture, when we have space is up and sorry, time is up and space is horizontal direction, everything that is points that are inside the light cone or at the light cone, they are in the causal future. Similarly, causal past, that is the points in the space-time that are inside the light cone in the past direction or are on the light cone. Then there's a definition that is very similar to the definition in Riemannian geometry, where we assume often that the manifold is complete. In Lawrencian geometry, one assumes that the manifold is globally hyperbolic, which says that there are two conditions. First is that there are no closed causal curves, so no time traveling in the space-time. And the second is that these causal diamonds, like in this picture, that are future of one point intersected with past of other point. They look like this kind of diamonds. They are called diamond sets, causal diamonds. We assume that those are compact. This basically means that you cannot go from P1, go and touch the boundary of the space-time and return back. So that's what it means in practice. If the manifold is globally hyperbolic, then it can be represented as a product of time, axis, and space. And you can think that you have a time-dependent metric on space, and you have well-defined time axis. So with Kurlev and Ullmann, we considered this type of inverse problem, and later we improved the result a little bit with Ullmann and Wang. And this concerns now four-dimensional space-time. So that we have three space variables, one time variable, and we consider the following type of picture. We have a time-like curve for instance freely falling observer, mu, and it contains 2 points P1 and P2. And we do measurements in a neighborhood V, this blue set here that contains this mu. We do measurements here. I like to think this kind of science fiction way of example, when you would have a spaceship that is falling in freely, so it moves in time, and we do measurements close to this spaceship. That is the neighborhood V. Then we consider the source to solution map for nonlinear wave equation that takes in a source F that is supported in this small neighborhood V. So we activate some measurements, some sources close to our spaceship. So this produces a wave that propagates to the space, time, and returns back. And we record the solution in this neighborhood V. This is well defined for small sources. We need to use so small sources because this equation is nonlinear. So for large sources, it can blow up in finite time. We assume that sources are so small that you don't have a blow up. Similar type of results are actually studied also for Einstein equations. And in this case, the smallness means funny thing. It means that we assume that we use only so small measurement sources that they don't create black holes. So that is the criteria of smallness. So it's not very restrictive. So anyway, we assume that we know this set V, this neighborhood of a path mu, and the source to solution map. Then we can reconstruct the domain where the waves propagate and return back. So this is the set W, that is the causal diamond, that is the intersection of future of P1 and past of P2, so this large diamond here. And we can reconstruct the metric on this set up to change of coordinates. This reconstruction of the conformal class was done with Kurlev and Ullmann, and the reconstruction of the conformal factor was part of our work with Ullmann and Wang. Like in this picture, the diamond set looks very simple, but for complicated space-time, the topology of this causal diamond set can be non-trivial. And this has also been recently studied for direct mappings by Hinch and Ullmann and Tsai. So what's the idea? We are considering interaction of waves. So let's consider this wave equation plus a simple nonlinear term. And to consider fourth order nonlinear interaction, we will consider 4 plane waves. And I explain this soon in detail. But when the waves propagate, they start to interact. I will soon show a video of this. 2 interaction doesn't lead to anything interesting. When all of the waves start to interact, then there is an interaction. This produces a point source, and the point source produces a spherical wave that propagates to all directions. So the interaction of nonlinear interaction of plane waves, or distorted plane waves, because they are not really planes, when the space-time is varying, they create artificial microlocal point sources. And from these observations, from the observations from point sources, we can determine the conformal mass of the metric in the domain where the waves can propagate and return back to the domain where we do measurements. So that is in the causal diamond. And also the conformal factor to the whole metric tensor can be reconstructed for this equation in 4-dimensional spacetime. So let's consider the basic methods how to study this problem. Again, here the basic message is that nonlinearity helps in solving the inverse problem. Let us substitute the ansatz, just the transformal power series, to this nonlinear wave equation. Now we consider this wave equation basically we assume that the waves vanished before time t is equal to 0, and then we consider the wave equation on time interval 0 to t capital. This is a finite time interval because the equation can blow up when you go to very large times. And we assume that the source is epsilon times some function f1. So we have this source is multiplied by parameter epsilon. Then we substitute this ansatz to this equation and see what type of equations we get to different overs of epsilon. We will see that the leading order term of this solution U, this W1 here, it satisfies a linear wave equation. So we use Q, that is the inverse of the wave operator, linear wave operator. You see that U is the solution produced by this. Sorry, W1 is the solution that is produced by source F1. Then when we look to next order term, it can be physically considered that the wave is interacting with itself. Sorry, here is now coefficient A also. This is also like measures the strength of the interaction. So the wave interacts with itself, produces an artificial source, and this is observed in the second epsilon power 2 term. To consider epsilon to power 3 terms, then we have the wave interacts with itself, produces a source that produces a wave. It interacts with this wave, interacts with the wave, produces an artificial source, and again produces a wave. And here we have this kind of wave interacts with itself, and it interacts with the wave where wave has interacted with itself. This is second order interaction. They interact and produce fourth order interaction. This produces an artificial source that then is visible in this term epsilon power 4, W4. And there also is a similar other term from different order of interactions. This is a little bit quite closely related to writing Feynman diagrams, so that you somehow see that what type of interactions appear. And then there's some residual term that is small. Let's consider these different order interactions. But before that, let's consider what type of waves one considers. Let's consider in space-time, let's change the coordinates. Let's not use the usual space and time coordinates. Let's use the coordinates for which the planes xj is equal to 0 are light-like. And these examples are now done in flat Minkowski space, so that this is a globally defined plane. Then we consider a plane wave that is the positive part of xj component. One more thing, so about the notations. Differential geometry, the indices of coordinates are put up. So this is coordinate x with index j, not x to power j, but jth coordinate. So we have the positive part of the jth coordinate to power m, and this can be written as an oscillatory integral, like this, where this function b here is a symbol in sense of Herminder. So this is technically what type of tools we use. We write plane waves as oscillatory integrals, and they produce this type of waves that look a little bit that one moment they can be like a plane wave or a piece of spherical waves, and later time moment it is different plane or spherical piece of sphere. And we are considering introduction of those. Let's consider this case when we have flat plane waves. The two waves interact with the intersection of two planes. Three planes interact with the intersection of the three planes, and four waves interact on the intersection of four planes. So here should be K4, sorry for the misprint. Now in four-dimensional space-time, intersection of three planes is a line, and intersection of four planes is a single point, like in this picture. We are going again to use the fact that when four plane waves interact, they interact interestingly at a single point, and this produces a point source in space-time. This picture here is just in 1 + 2 dimensions, but now we are considering 1 + 3 dimensions. Okay, so how we do these different orders? Let us again consider interaction of two waves, or like we have a linear combination with small parameters epsilon1 and epsilon2 of two sources. Then the second order interaction is that we take solution of the nonlinear wave equation and differentiate it with respect to different epsilon parameters, and we get this term, where this u1 and u2, they are solutions of the linear wave equation. By using results, for instance, by Greenling and Van Uhlmann, one can see that okay, some interaction happens, but it doesn't produce any singularities that would propagate to new directions. So the two wave interactions are not interesting. What happens for the interaction of three waves? So let's consider again three epsilon parameters. They are used to compute the linear combination of three sources. Then we have a solution of the nonlinear wave equation corresponding to this source, and we differentiate the solution with respect to all epsilon parameters once. We start to get this type of series. So we have waves number 2 and 3 are interacting. They produce artificial source. This artificial source produces a wave. We saw the wave equation, linear wave equation. And then this interacts with the wave number 1. This product here is a new artificial source. And we saw the wave equation, and then this gives us W3. And now this artificial source here is supported on a line in space-time, and it produces some interesting singularities. Let's see what it means. So actually, what is a line in space-time? Line in space-time is actually the path of a moving point source. So if you have a point source that is moving in space-time, so that you would somehow think, for instance, analogous case when you have an airplane that is moving very, very rapidly. and it is moving actually extremely fast. So it's moving faster than other waves on the manifold. So geometrically, it produces. It is a source that produces something that is very similar to a shock wave that is produced by, for instance, a ultrasonic airplane or a bullet that moves very, very fastly. So this is not really a shock wave, but it looks geometrically like a shock wave. So what happens? Here are three plane waves. They start to propagate in time. Now they start to interact. Nothing first happens. Then all of them start to interact. Interaction is on and on and on and on. Now like this. They produce some wave and then stopped, and then the interaction wave propagates. We had a point source that was on a long time and was moving very, very fastly, so it produces a conic wave. This is very similar to this shock wave produced by ultrasonic airplane. At least that is my intuition of what happens here. Let's see. Yes, so I just do this again. So, okay, the three waves are here. They start to propagate. Now they start to interact. Interaction is on. It stopped, and they produced a wave, this black conic wave that is propagating in space. Similar to the fourth order interaction is that we have 4 epsilon parameters. We take a linear combination of 4 sources with weights epsilon j's, have a source f epsilon vector. This corresponds to the solution u epsilon vector of the nonlinear wave equation. We compute its fourth order derivatives, evaluate everything at epsilon is equal to epsilon are equal to 0. And this produces a point source that is essentially, that has important singularity at the signal point. So when 4 plane waves intersect, an artificial point source appears. Why this? What this means technically? This next slide is very technical. So for this equation here, the fourth order interaction action term, that is the derivative of the solution with respect to all epsilon parameters. It is the solution of the wave equation with artificial source S, where S is the product of 4 linearized waves. Okay, what this means, each of these linearized wave is now written as an oscillatory integral. And I just multiply those together and write that as an integral over R4. So all of these integrals, I just like use Hubin's theorem basically, and I write it as integral of R over 4. I collect all phase functions together, like here. All these symbols are multiplied together to get one symbol. And we actually see that this can be considered that there's a pseudo differential operator operating to a delta distribution. So the pseudo differential operator doesn't change the wavefront set of the delta distribution. So microlocally, this is just a delta distribution. So this fourth order interaction term, that is the wave produced by this S4. S4 is microlocally very similar to a delta distribution. So this W4 is very similar to the fundamental solution that is produced by the delta source. Now we just have a slightly modified delta source. And I want to mention that, okay, here for this equation, when we had this fourth order nonlinearity, like this, the computation was relatively simple. There are some small technical difficulties. Oops, now I went the wrong direction. When you analyze these more complicated products, then you have to work a little bit with somehow estimating what are the properties of products of conormal distributions. But basic idea is like this: the fourth order interaction produces something that is very similar to delta distribution. Okay, so what happens now? This was now this picture. We have where we have video with four plane waves. They start to propagate. First, two wave interactions appear, but no new singularities are appearing to any interesting directions. Like this, then the third order interaction starts. Now fourth order interaction happens. It is like point source. Rapidly, at some moment, there's delta distribution in space and time. It produces a spherical wave that goes to all directions. So we send basically four waves that propagate along four geodesics. All of them intersect at single point, and this produces an artificial point source in space-time that is actually observed. It also returns back to this area where we do measurements. So basically, we can fill the space-time with artificial point sources. The next question is that how we could use these point sources to do reconstruction of space-time. And we can now forget all the waves, and we can think that we have just space-time where there are lots of point sources. Are there actually any questions related to this earlier part? Okay, let me continue with this. Now, again, a slightly different inverse problem. We have a space-time, and we are considering passive observations. So let me motivate these passive observations that actually the whole astronomy is passive observations. We are observing things that happened a long time ago on the sky, and they are very interesting phenomena. For instance, there are this type of gravitational lensing that happens with very long distances. That there's, for instance, a picture of one quasar that's called Einstein's cross. There are like one object looks like five objects, and that is extremely far away, and it is behind the gravitational lens. So there is some very massive object between us, the observer, and the original source. And the light has came along several different directions. So the massive object, maybe some groups of galaxies here, they have operated as like a lens. And also, it's actually very interesting that in this picture, the time that the light has taken to travel along different roads can be very, very different. That it can be even like the light. See that if here is some variation of the source, light comes with different roads. The difference of the time, how long it takes to travel along these paths, the difference can be several years. So these are not now the time scales that we are considering. That when we have like observations and we see light coming from along different geodesics, we are measuring the distance, the difference of these travel times, and the time units are years. Also, in addition to these optical observations of light or X-rays, we can also consider gravitational waves. They propagate similarly, and then there are these very famous detection of gravitational waves. And nowadays they are actually improving this methodology. They speak about gravitational wave astronomy. So basically, they really can somehow like get information what happened by considering measurements, more precise measurements of this of the gravitational waves. How to somehow get an intuition to this? This is actually a funny picture. There is a image from astronomical observation. The light comes as a ring. This is called Einstein's ring. And you can somehow see this the same when next time when you are in a party, you can explain what we are doing. You can somehow take a wine glass, you point it to a light source, and then you start to see this ring-like structures. So the wine glass is somehow is a lens. It's bending light in the same way as massive objects are bending light. and creating these Einstein rings in astronomical observations. So there was a LED, bright LED on the wall, and the person was looking at the LED through a wine glass. So the wine glass is now, you're looking from just straight from the bottom. Okay. How to model this kind of passive observations from point sources on a Lawrencium manifold? Let us consider this type of setting. We have a open set V, that is neighborhood of a time-like path. And we assume that this set where we do observation, this is union of time-like paths, like all this union of this type of red curves. Physically, so this set V is in space-time, and these red curves, they could be the roads of the satellite when the satellite is freely falling in close to Earth. So you have lots of satellites that are doing measurements. And because they are in different positions, they observe things slightly differently. Let's now take like this one path. I take path number A0. The paths are indexed with index A. And I take two points P1 and P2. And I consider an unknown part of spacetime, U, that is in the past of the point P2, but not in the past of P1. So we could think that we are doing measurements close to Earth, and we are considering some distant galaxy, like Andromeda, and some time interval in the lifetime of Andromeda that is in this region. And then we assume that there are lots of point sources. Let me discuss physicality of these point sources a little bit later. But let's now just mathematically consider that we have lots of point sources in this open set U. So U is open set, relatively compact set in this domain, and there are lots of point sources. So when you have a point source at point Q, it sends a light signal that propagates along the light cone. And the light cone intersects the area where we do measurements. And actually along each of these satellites, this path mu A, every mu A observes when the light from point source Q has arrived. This is called the observation time function, FQ. So you have a point source at Q. A is the indexing of these red paths along which we do observations. And the function FQA, this is the minimum minimum value of S, so that there is a light-like geodesic from Q to mu A of S. So this means that this FQ of A, this is the first time when we observe light coming from a point Q on a path mu A. So this just means that you see somehow like say you would see that a nova in Andromeda or some rapid change, and then you have lots of satellites close to Earth, and you are observing the satellites when the signal from this sudden event arrives. And this is our result with Kuriliv and Ullman. So we have a globally hyperbolic Lorentzian spacetime. We assume that the geometry is like in this picture that we do observations in set V, this union of time-like paths. We have 2 points P1 and P2. There's unknown portion of the spacetime, this distant galaxy, that satisfies this condition, like in this picture. Then, if we know, we are given the neighborhood where we do observations and the metric there. We are given these paths, mu A's, so these are all close to Earth. And then we are given the collection of all observation time functions. So for all point sources Q that are in this domain U. Then we can reconstruct this set U up to change of coordinates, and we can reconstruct the conformal class of the metric in U. So in very rough terms, we do observations in satellites, mu A's, close to Earth. We are observing some distant galaxy. There are lots of point sources. and then we can reconstruct how the conformal class of the metric. The metric is actually the gravitational field of the spacetime in this region. Okay, what's the idea of the proof? It is very similar to these boundary distance functions. We consider the collection of all time observation functions. One can show that this collection of the time observation functions as a subset of continuous functions on this index set A, that index is the paths, mu a's, these are homeomorphic. Then we can consider at near a single point, we can consider we can take, like in this picture, we take we take here in this picture, we take 3 paths. In 4-dimensional spacetime, we would take 4 paths, there are 4 satellites, and the time when each of the satellites observes light coming from Q, this gives one coordinate of point Q. These coordinates are well defined, and we can detect what coordinates, what paths define good coordinates and which doesn't. And then we can see how the images of light rays looks in these measurement coordinates. And those light rays, images of light rays, they determine the conformal type of the metric on this set. So this set, the collection of all observation time functions, this is a manifold that is homeomorphic and diffeomorphic to the original manifold, and there we can reconstruct the conformal type of the metric. So we can reconstruct a copy of the original. We can reconstruct a copy of this region of the spacetime. Then we can reconstruct the metric tensor up to a scalar factor. So what would be possible applications of this type of theorems? If you consider now just pictures from sky, the point sources, of course, you have some idea of that what surely is a point source. For instance, a supernova is surely a point source. And there are many supernovas when you are doing measurements over very long time periods. But also there are lots of varying stars, like flare stars and stars that produce some rapid variations. So here is a classification of all stars, how the stars are somehow. So here's like a main sequence, how the stars are behaving when they get older. I think I don't remember now where our sun is. What is the location on this chart of our sun? It's somewhere in this main sequence. But anyway, even stars in the main sequence, they become flare stars, so they start to produce rapid changes of luminosity. And this could be maybe considered as point sources, because they are relatively fast changes. And now the timescales that we are considering are years. All these white areas here are stars that the astronomers classify as varying stars. So they could maybe be used as point sources. Okay, let me say a few words what's happening just now. So with Ali, Face, Mohammadi, and Oksanen, we were able to consider inverse problems when we use only interaction of 3 waves. So when the 4 plane wave intersected, then they produce the point source. When interaction happens with 3 waves, this is a little bit more complicated. But but still, these 3 wave interactions are happened more. They are not so much depending on the dimension of the space. So we can solve inverse problems in all dimensions, 1 plus n, when n is larger than 2. And one can also consider, at this moment, we are considering polynomial nonlinearities. If generally the local measurements, the short solution map, determines the conformal class of the metric in a causal diamond, and in many cases, so many now means that if the dimension of the space, when you have the space time has dimension 1 plus n, so n is dimension of the space. If dimension of the space is not 3 and the nonlinearity is not 3, then the conformal factor of the metric can be also determined. So we can determine the whole metric up to an isometry. Also, we can consider the cases when we have non-local measurements. Sorry, we have separated measurements. The sources are supported in one portion of the space-time, and we do observations. The waves are observed in other part of the space-time. And in this kind of configuration, so just important that the last point here, its future is not intersecting the area where we do measurements. And here the first point, its past is not intersecting the area where we do where we have the sources. And this is this black box here is the domain where the waves can start somewhere in this omega in, and then they can travel in the space-time and return to omega out. So this black box here, this diamond, causal diamond, this is also a causal diamond set. This is the best area that one would like to, one could in principle reconstruct, because waves can be produced and they can be observed. And one can also study a little bit more complicated this type of quasi-linear equations can be studied. Here the trick is that when we use these third order interactions, we have they produce artificial sources that are products of three linearized waves. And products of three linearized waves are so rich structured that they produce lots of singularities. That, like, for instance, there's this kind of picture that when three plane waves intersect, if they intersect just in right way, then they produce a source on a line, and this line type source produces this type of red cylinder that starts to propagate to different directions. Here the main point is that this cylinder produces waves that also propagate back to the direction where these planes came from. And actually, it was interesting when we made these videos to present this thing. We thought that, let me go back to this video to tell about mistakes related to presentations. Let's see, it should come soon. Something is. Anyway, when we have this interaction of three waves that produces this conic wave, that is this configuration that was very easy to compute by hand. Then the conic wave goes to the directions that are far away from the directions where the plane waves came from. So we thought that this is just something that we cannot use. But then when we made better computations, something is happening. So, okay. Let's see, something is with this Acrobat really is problems. So maybe I have to stop sharing for a second. Do it. Sorry, there's some technical problem. Just one. So anyway, let me. Sorry, I have some technical problems with the computer. Okay, now it should work again. Okay. So when we made a better analysis, we noticed that we can send waves. We can these three interactions sends waves that we can use to solve the inverse problem. For instance, like here is a simulation of three plane waves that come from very close directions. They start to propagate, then they start to interact, and they produce a conic wave that sends waves back to the area where we sent those. So this was the key observation, that actually these three wave interactions give enough singularities that by slightly varying these directions of this, when we slightly vary these initial positions of these plane waves, we can rotate the cylinder and send singularities to the area where we do observations. Okay. Maybe I say just very few words about inverse problems for elliptic equations. This principle that nonlinearity helps in imaging, that can be also used to study elliptic equations. In the case when in the cases that are still open for the linear problem. For instance, in this work that we did with Liimatainen, Jieshuan, Lin, and Salo, we were considering nonlinear elliptic equation with Laplacian in Rn plus nonlinear term, and the corresponding linear problem would be that here m would be 1. Then we assume that we have both unknown potential q and we have an unknown cavity in the domain. So there's a hole, a cavity d in the domain, and we assume that we have the equation in omega minus the cavity. On cavity we have Dirichlet boundary condition, and we can control the boundary value, the Dirichlet boundary value on the exterior boundary in the domain omega, boundary of omega. And then we do measurements only on the boundary of omega, so we map this f to the Neumann derivative of the solution on the exterior boundary. And now it turns out that for this nonlinear equation, we can determine both the potential q and the cavity. And this problem is open for linear equations. So if m would be 1, then you can solve this problem if you assume that let's see. Even in the case when that even if you know that when the cavity is known, then this is very difficult partial data problem. But anyway, this problem of finding both the unknown coefficient and the cavity, this is open problem for linear equations. So nonlinearity helps also solving the elliptic equations. And maybe I mentioned this, that for in a two-dimensional case, one can consider similarly, you have unknown metric, unknown potential, and unknown manifold. And then when you consider the Dirichlet to Neumann map on the boundary, then you can determine the manifold. You can define the conformal structure of G, and then actually so you can determine the conformal class of G, and then the conformal factor of G and Q are determined up to a gauge transformation. So again, you can study some problem that is unsolved for linear problems. And if I say very quickly about the proof, the idea of the proof is that the key point is that you consider again a higher order Fresnel differentials of the map, the Dirichlet to Neumann map, and when you compute those, then you will get integrals of the unknown function, this potential q, and several waves. Several solutions. And the main point is that the solutions satisfy equation without any potential. And in roughly speaking, it is enough to do research where all difficulties are related to the linearized problem with no potential. So just for harmonic functions. So roughly speaking, we can do analysis for linearized inverse problems in the same way as Calderon started this field of inverse problems for multidimensional equations, and we don't require even this more complicated Sylvester-Ullmann type of analysis. And for this comment, the end was very quick, but I wanted to give you a flavor. So thank you very much for your attention. Thank you.
Thank you very much, Matti. Any questions?
Hi, Matti. This is Jim Peng, and I would like to ask a question. You mentioned there's a result for the on the reconstruction of the manifold from boundary distance functions for non-compact manifolds.
Yes.
Um,
How is that formulated, specifically considering that the length is infinite, maybe infinite?
Oh, sorry. I said okay. That means that something happened again. Yeah. So that we have you could have a non-compact manifold that is complete in the asymmetric space, and then it has no non-empty boundary.
Mm-hmm.
Yes.
So I mean, how the result is formulated, because for non-compact manifold the distance may be infinite, and do you include the infinite part of the points?
Yes.
I mean, if you know all the boundary distance functions, for example, there could be a part of the manifold such that the distance between this part and the boundary is infinite. So how would you formulate this thing?
So let's see. So yes, we assume that there's only one component, so that every 2 points have a finite distance, but this distance can be arbitrarily large. So let me now I can share this. Yes. So and I hope that I was not confusing with this this question. So that if you consider this problem, when we have like these kind of point sources that go off, often we don't know what is the time when these point sources go off. So we don't go the time. We don't know the time physically when the point sources becomes active. But in this talk now, I assume that we know what is the time when the point source become active.
Mm-hmm.
So this means now that when we are considering these distance functions, we assume that this t0 is 0. So we are given this star is 0. So we assume that we are really given this this distance function. And now what we can do, for instance, we can say that let's only take those boundary distance functions for which minimum value is less, for instance, than say 100. And this cuts the manifold. They correspond to part of the manifold that is a finite. So we start to say that let's consider subset of all boundary distance functions. Let's take those where the minimum is smaller than some constant.
Mm-hmm.
Then corresponds a finite layer close to the boundary.
Mm-hmm.
We construct that, and then we take next layer. So that is the technique.
Yeah. Okay. Yeah. I see.
Very nice question. Thank you.
Thank you.
Any other questions? So Matti, I have a question. So what about for time-dependent Lorentzian metrics? You know, the just before you finish off the elliptic one, you had this determination of the Lorentzian metric, right? And how about for time-dependent cases? Would those methods work, or is this like somehow related to the boundary control method?
So the techniques are now totally different. So the boundary control method is very much based on Tatarov's unique continuous result, and when we consider nonlinear problems, then we are considering how the products of linearized waves, how they look like. And that's why we don't use Tataros unique continuation at all. And the metric and all the coefficients can be time depending. There are no difficulties with that.
Oh, I see. Okay. But the results that you maybe for, did you just simply for simplicity just state it for time independent metrics? But
so there was now this thing that in Lawrencian geometry that is a little bit confusing, is that when we use the variable x. Sorry, something is wrong with my.
Okay. Got it.
Let me just answer, because if this was unclear for you, it must be unclear for all your all the big portion of the audience. So okay, there is this slightly confusing thing now. When we consider Lawrencian geometry, then we denote the coordinates of space-time by x. So x contains the first coordinate x0, that is the time. So even if I write x, this actually is like x and time.
Okay. Yeah. Okay, now I understand.
Clarification. I should have emphasized this a lot.
Yeah. Thank you very much. Yes. Any other questions? If not, so Matti, thank you very much for taking the time and giving 2 wonderful talks. So hope to see you in India or some other place sometime very soon. Thank you very much.
And thank you very much for organizing this wonderful event now during these times when it is difficult to travel. It's very important for the whole community. So thank you very much, Venki.
Thank you. Bye-bye.